Every year, countless gemstones pass unnoticed beneath people's feet. Not because they are rare, not because they are hidden, but because most people never learn how to read the landscape around them. To an untrained observer, this is simply a collection of rocks. To a field geologist, it is a record. A record of mountains being uplifted, rocks being fractured, minerals being transported, and geological processes that may have begun hundreds of millions of years ago. The remarkable thing is that many valuable gemstones leave evidence long before the gemstones themselves are discovered. A color, a texture, a crystal fragment, a particular type of rock, small clues that gradually lead to much larger discoveries. And our journey begins in one of the most effective natural sorting systems on Earth, a stream. Garnet. Water is constantly sorting the landscape. Every flood removes material. Every season reshapes gravel bars. Every current separates lighter minerals from heavier ones. And over time, certain minerals begin accumulating in predictable locations. An experienced prospector notices a narrow band of darker sediment trapped behind several stream boulders. It isn't flashy, it isn't colorful, yet places like this often deserve closer attention. Most of the material looks ordinary: quartz fragments, weathered rock chips, common sand. Then something catches the light. A sharp crystal face, deep red, almost translucent along its edges. Unlike the surrounding stones, it still retains part of its original crystal form. That survival is not accidental. Garnet is remarkably durable. While many minerals gradually break down during transport, garnets often persist, and that makes them excellent geological messengers. This small crystal may have traveled a considerable distance, but it originated somewhere upstream. Most garnets form within metamorphic rocks, such as schists and gneisses. These rocks were once buried deep within Earth's crust, where heat and pressure transformed their mineral composition. Over immense spans of time, tectonic uplift brought those rocks back toward the surface. Weathering eventually released the garnets. Streams then carried them into valleys below. For a prospector, finding a garnet is not necessarily the goal. The goal is understanding what the crystal reveals about the landscape. The next step is interpretation. Move upstream, compare gravel concentrations, search for additional crystals, look for exposed metamorphic bedrock. Piece together the geological story. Because geology rarely provides answers all at once. It reveals them layer by layer. As additional samples are examined, something becomes clear. The garnets are becoming more abundant. The source appears closer. But before the metamorphic rocks are reached, another discovery interrupts the search. A weathered stone lying near the stream bank. Completely ordinary on the outside. Yet what lies inside tells a very different story. Amethyst. Nothing about this rock immediately attracts attention. No bright colors, no visible crystals, no indication that anything unusual is hidden inside. The rock breaks, dust falls away, and suddenly the interior reveals something entirely unexpected. A chamber of crystals, delicate, sharp, deep violet in color, amethyst. Moments like this explain why geologists often examine broken surfaces instead of relying on weathered exteriors. Weathering hides information, fresh surfaces reveal it, and in this case, the fresh surface exposes one of the most recognizable gemstones in the world. Amethyst is a purple variety of quartz. Its color develops when trace amounts of iron become incorporated into the crystal structure and are later influenced by natural radiation within surrounding rocks. The result is the distinctive purple coloration collectors immediately recognize. But the real geological story began long before the crystals appeared. As volcanic lava cooled, trapped gases created empty cavities. These spaces remained hidden within the rock. Later, mineral-rich hydrothermal fluids entered those openings. Over thousands of years, quartz crystals slowly grew inward from the cavity walls, layer by layer, crystal by crystal, until the empty space became a natural crystal chamber. For prospectors, the lesson extends beyond amethyst itself. Finding one crystal cavity suggests geological conditions worth exploring further. The next step is examining nearby outcrops, searching for additional cavities, identifying quartz-rich zones, mapping the extent of the volcanic host rock. looking for recurring patterns across the landscape. Because one cavity may be interesting, a cluster of cavities becomes a geological target, and there is another reason geologists pay close attention to quartz-rich volcanic systems. These environments preserve more than crystals. They preserve part of the region's geological history. The same process is capable of creating spectacular amethyst can also point toward entirely different mineral environments nearby. Environments form much deeper underground, gemstones born not from volcanic cavities, but from the final stages of crystallization within cooling magma. Topaz. From a distance, these granite ridges appear solid and uniform, but a closer examination tells a different story. Notice the unusually large mineral grains: quartz, feldspar, mica, each crystal clearly visible. This texture reveals something important. The magma that formed this rock cooled very slowly, and near the end of that cooling process, something unusual happened. The remaining mineral-rich fluids became concentrated within fractures and pockets. Imagine the final few drops left in a slowly evaporating pot. Those remaining fluids often contain ingredients capable of growing exceptionally large crystals. Geologists call these zones pegmatites, and some of the world's finest topaz crystals originate within them. Rather than climbing immediately toward the outcrop, the prospector studies the slope below. Years of weathering have loosened fragments from the pegmatite. Rain has carried them downhill. Gravity has spread them across the surface. The hillside has been quietly sorting material for decades. Then something catches the sunlight. A crystal, partially exposed, clear, angular, still preserving several natural crystal faces. Unlike the surrounding rock fragments, it reflects light with remarkable clarity. The crystal is carefully lifted from the soil. Topaz, a gemstone that often survives long after its original host rock begins breaking apart. Its hardness allows it to resist weathering. Its crystal form frequently remains recognizable. And for prospectors, discoveries like this provide an important clue. Not necessarily about the crystal itself, but about what may still exist higher on the slope. A loose crystal rarely tells the entire story. Its significance comes from context: where it was found, which rocks occur nearby, how weathering transported it, and whether similar crystals appear elsewhere across the landscape. This is why professionals compare specimens, identify host rocks, trace pegmatite exposures, and reconstruct the sequence of geological events that produce the crystal in the first place. Because every gemstone is ultimately part of a much larger geological process. Emerald. This type of geological setting attracts attention for a reason. Some of the world's most famous emerald deposits formed where very different rock types met and interacted. Emerald belongs to the mineral family known as beryl. Its vivid green color comes primarily from trace amounts of chromium or vanadium. But what makes emerald especially fascinating is how difficult it is to form. The ingredients required for emerald rarely occur together naturally. One rock may contain beryllium, another may contain chromium. A geological process is needed to bring them together. Hydrothermal fluids often perform that role. They transport chemical elements through fractures and structural pathways. Under the right conditions, emerald crystals begin growing within the surrounding rock. This is why prospectors carefully examine contacts between contrasting rock types. Not because emeralds are visible everywhere, but because the geology suggests the possibility. The gemstone is only part of the story. The environment that created it is often the most important clue. As the investigation continues, the altered zone gradually disappears. But another geological feature begins to dominate the landscape: a pale crystalline outcrop emerging from the hillside. Bright, massive, and unlike the rocks surrounding it. The green trail has led somewhere new, and hidden within this marble lies another gemstone formed under extraordinary conditions. Ruby. The outcrop itself appears relatively plain, white, crystalline, almost featureless from a distance. Yet prospectors often examine weathered material below marble exposures very carefully. Because erosion frequently releases durable minerals from their host rock, most fragments reveal nothing unusual. Then a small flash of color appears: deep red, sharp-edged, partially exposed, just enough to catch the sunlight, a crystal hidden within the marble. Ruby. Few gemstones are as recognizable, and few form under such specific geological conditions. Ruby is the red variety of corundum. Its color develops from trace amounts of chromium incorporated into the crystal structure during growth. The story begins as ordinary limestone. Over millions of years, burial, heat, and pressure transform that limestone into marble. Under the right chemical conditions, corundum begins to crystallize. If chromium is present, ruby forms. For prospectors, discoveries like this create new questions. Is this an isolated crystal or part of a larger ruby-bearing zone? The answer requires studying the host rock, comparing samples, and reading the geological setting as a whole, because gemstones rarely occur without context, and the context often reveals where additional discoveries may be waiting. As fragments weather from the hillside, streams begin carrying some of the most durable minerals away from their source, including corundum, which means the next clue may no longer be inside the mountain. It may already be downstream. Sapphire. The water here looks familiar, much like the stream where our garnet journey began. But this drainage carries material from a very different geological environment. Again, the current performs its constant work, sorting, concentrating, separating. Lighter minerals continue downstream, heavier minerals settle. The result is a natural concentration of durable crystals, dark sands, dense mineral grains, fragments of quartz. Then something unusual appears, a flash of blue, small, transparent, distinctly different from everything around it. The crystal is carefully washed and examined. Sapphire. Like ruby, sapphire is a variety of corundum. The difference comes from trace elements incorporated during crystal growth. Those small chemical differences create entirely different colors. Because sapphire is extremely resistant to weathering, it often survives long after surrounding rocks have broken apart. Streams transport the crystals. Nature concentrates them, and prospectors learn to recognize the locations where those concentrations develop. Finding a sapphire is exciting, but geologists immediately ask another question. Where did it originate? The search expands. Drainages are compared, sediment concentrations are evaluated, and slowly the landscape begins revealing the path back toward the source. But before that source can be identified, the terrain changes once again. The mountains fade behind us. The environment becomes drier, and another geological story begins. Opal. The rocks here look completely different. No marble, no metamorphic outcrops, no crystal-rich pegmatites, just weathered sedimentary layers stretching across the landscape. At first, nothing appears unusual. Then a brief flash of color, almost too quick to notice. Blue, then green, then red. Gone again. The prospector stops, turns back, and examines the rock more closely. The surface breaks apart. Inside, another flash appears, stronger this time. Opal, one of the most visually distinctive gemstones on Earth. Unlike ruby, sapphire, or emerald, opal is not built from large crystal structures. Instead, it forms when silica-rich water moves through cracks, cavities, and porous rock. As the water evaporates, microscopic silica spheres remain behind. Over time, these structures interact with light in extraordinary ways. The colors seem almost unreal. Yet they are the product of a geological process that unfolded over immense spans of time. And once again, the discovery is only the beginning. The surrounding rocks, the silica-rich zones, the distribution of color-bearing material. Together, they help reconstruct the geological history of the area. 4 gemstones, 4 entirely different geological environments. Hydrothermal systems, marble-hosted deposits, stream concentrations, silica-rich sedimentary settings. Yet each discovery emerged from the same process. Careful observation, patience, and a willingness to let the landscape reveal its story. But the investigation is far from over. The remaining gemstones become even more unusual. One forms inside giant crystals. Another develops in copper-rich environments. And one has fascinated civilizations for thousands of years.